Hello, my name is Muhammad Afzal bin Azmi. My matrix number is AA190379. I am from section 5. Today I want to explain about additional theory of experiment 1. So number 1 is metallic and ceramic materials utilized in mechanical engineering applications have crystalline structure. Number 2, the crystals are formed from a liquid which is a solution of molten solid or a gas in which particles are randomly oriented. Number 3, different materials may have the same unit cell and crystal structure, but they will not have the same lattice parameters. Number 4, crystal structures are quite lengthy, for they are so small. They have their own measuring unit, which is called the angstrom. And lastly, the radius or range of the atoms is mu over when we take a look at the lattice parameters. Next, I want to explain about the objective of the experiment 1. So number 1 is to identify the types of solid materials according to the atomic arrangement and structure. Number 2, to determine the atomic packing factor for every each of structure that we use in the experiment. Number 3, to investigate about the unit cell of a crystal structure. Number 4, to determine the suitable formula to calculate the atomic packing factor for each crystal structure. And lastly, number 5, to analyze the pattern of the structure of the material used in the experiment. And then I want to explain about the apparatus of experiment 1. So number 1 is we use styrene balls act as an atom, and number 2 is connection rods will act as space lattice that connect atom to another atom. So this is the diagram of the apparatus.
Bismillahirrahmanirrahim. My name is Muhammad Ibn Mazaturi. My number is AA191344. Okay, today I will explain you about my group experiment, and my part is procedure and result. Okay, my group experiment is atomic arrangement in the solid structure and the crystal structure. Okay, before start the experiment, we must know the procedure before we doing the experiment. So after we doing the experiment with the true procedure, the experiment will be easy and the result will be success. Okay. Next, first procedure, we must connect the strings ball with connection rod. Okay, we must get the strings ball and connection rod. Okay, to the first step. And second step, arrange the strings ball and combine the strings ball and the connecting rod until get the simple Rubik's structure. So the second, you must get the strings ball and connecting rod and combine the two items until get the simple structure, simple Rubik structure, or more specific, simple Rubik model. Okay. 3. Easy. Repeat step 1 until step 2 until you get the simple Rubik structure, and you can build base Rubik, face center Rubik. That you until step 1 until step 2 you repeat until you get the center Rubik. Okay, 4. Observe the model to describe the start of void for the model. For void, you must observe the model to describe until you get the void for the model. Okay. 5. Classify. You must classify the result of observation this is important. You must classify the result of observation into tetrahedra. Remember, tetrahedra void, tetrahedra void, or octahedra void. The two you must remember. And 6, you must record the observation for your next experiment, or record your observation for the result. Okay. 7, by using the sum model, rearrange the sphere, make sure it is to axes are vertical. So the next step is you must observe the model, the same model until you get the sphere model. Make sure two axes is vertical. Okay. 8, observe to the model and make comparison between the observation. So you must compare the Rubik model and Spera model to you get the observation. Okay, 9, you must record the observation. And then lastly, determine the void for both observation. So you must determine the void of two observation. Who observation more better? So my presentation procedure is done. Now you see the result. Okay. If you see the result, the first, we must know the formula for this atomic packaging structure formula. APF equal to N VA per VC. So we must for calculation. One is simple cubic. You get the result or get the information in the formula and you get the answer. And second, same, third same, and four is the same too. So you can get the answer, the result will better in the atomic packing factor. Okay. Thank you.
Hello, Assalamualaikum. My name is Muhammad Aiman Ashraf bin Muhammad Zani, and today I will explain to you about the observation and conclusion for the atomic arrangement in the solid structure and crystal structure. First of all, we will go through to the observation first. Firstly, simple cubic lattice consists of one atom in unit cell, and body-centered cubic lattice consists of two atoms in unit cell. Face-centered cubic lattice consists of 4 atoms, and hexagonal close-packed lattice consists of 6 atoms in unit cell. Atomic packing factor for simple cubic, body-centered cubic, face-centered cubic, and hexagonal close-packed cubic can be calculated by using APF formula. For simple cubic, 52% of cell unit space is filled with atoms, while 48% is red. For body-centered cubic, 68% of cell unit space is filled with atom, while 48% is void. For face-centered cubic, 74% of cell unit space is filled with atoms, while 26% is void. For hexagonal close-packed, 74% of cell unit space is filled with atoms, while 26% is void. That's all for the observation. We will go through to the conclusion and recommendation. In the nutshell,
We gain knowledge about how to identify the types of crystal structure in solid materials. We get to know the estimal shapes of a crystal is controlled by its internal structure. Crystals are composed of atoms arranged in repeating patterns that can have 2, 3, 4, or 6 fold of symmetry where each repeating pattern is located at a lattice point. Next, a three-dimensional crystal lattice is a structure formed by countless number of identical and tiny building blocks that we call as a unit cell. Furthermore, when we identifying the crystal structure symmetry, we should know that the angles between faces are more important to consider than the absolute sizes of its individual faces. As a condition during the growth of a crystal prevent faces from developing as perfectly they could be or from developing at all. Other than that, we learn about calculating and investigating about the atomic packing factor for the structure. The atomic packing factor can be defined as the fraction between the volume of the basic atoms of the unit cell in a crystal structure that is occupied by constituent particles. The three relative simple crystal structure that we investigate in this experiment has its own method to calculate the atomic packing factor. We would recommend that we have to calculate it carefully, such as using the formula carefully to get the atomic packing factor for the material that we are trying to find. Besides, we would recommend to calculate it 3 times to confirm that the answer we get are correct. So that's all from me. Thank you.
Hello, my name is Muhammad Sharul Izhar bin Zulkifli, and now I'm here to describe about the discussion of this experiment. So, for the question A, a simple cubic. In the simple cubic structure, there is only one lattice point at each corner of the cube shape unit cell. They mark the position of either a single atom or the same group of atoms, known as the motif, which is repeat across lattice. The simple cubic structure with only one atom per lattice point is relatively rare in nature, as it is fairly unstable because of its low packing efficiency and low number of nearest neighbor around each atom. Polonium Pe is reported to crystallize in the simple cubic structure. So, for the question B, base center cubic. The base center cubic structure is based on the simple cubic structure, but has an additional lattice point at the very base of the cube. The packing efficiency and the nearest neighbor interaction are slightly higher than for the simple structure, so it is more common in nature. Bromine metallic solid with this structure are iron, chromium, and tungsten. So for the question C, in this crystal structure, there are the 8 lattice points at each corner, as in the simple cubic, but the additional lattice point at the center of the cubic. This structure is very common for metallic elements, as it maximizes the packing efficiency and the highest number of nearest neighbor, increasing its stability. So, for the question D, hexagonal closest back subtool. It has a coordinate number of 12 and contains 6 atoms per unit cell. The third layer contour instead. The third layer repeat. The fourth layer is the second layer repeat. The fourth layer is the second layer repeat, and so on. The hexagonal close pack crystal subtool include cadmium zinc and a phase of titanium. So that's all from me. Thank you.